Okay, so in this video, we are going to be looking at something I'm sure you all saw in ECE 35, and that is the Phasor method for sinusoidal steady state RLC circuits. Okay, so the sinusoidal just means that the inputs that we put into these circuits are going to be sinusoids. And the steady state means all the transients have passed. Everything is just really nice for us to study. Everything in the circuit is going to be sinusoidal. And the RLC just means that there are resistors, inductors, and capacitors only in our circuits. Okay, so that's the general setup for what we're going to talk about. But first, I'm going to show you the general setup that we're going to be kind of looking at broadly in ECE 45. And it's going to be almost comically general. So I'm going to have an input, and that's going to go into something, and I'm going to have an output. Okay, so this is kind of the main idea of a lot of what we're going to study in ECE 45. We have something, which we're going to call eventually a system, and we're going to have an input to that system, and that input is going to produce an output. Okay, so this is the general setup for a lot of what we're going to study in ECE 45. But in order to make a transition from ECE 35, we're going to first talk about this general setup specifically applied to the case where this system is an RLC circuit and this input is a sinusoid. Okay, so this is the general setup, and you'll see throughout the class we're going to keep getting more and more general. And even beyond this class, there's even more generalities you can make, but this is sort of what we're going to be looking at in ECE 45. And so now specifically, let's look at what happens when we're studying RLC circuits and sinusoidal steady state. Okay, so what happens then? Well, it's pretty much what I just said. This box here is going to be some RLC circuit. Okay, and our input, it's not just going to be anything, it's going to be a sinusoid. So how do we write a sinusoid? Well, that's what we're going to talk about right now. This is my input. So what have I written here? Well, I've written a pretty general sinusoid. And why is it general? Well, I have a lot of variables in it. So this variable A stands for the amplitude. That controls how much on the vertical axis the sinusoid is oscillating. Okay, so larger A, it's oscillating more, smaller A, it's oscillating less in terms of amplitude, the height of the sinusoid. What is this quantity right here, that omega? That is the frequency. Okay, and you can see that's multiplying this time variable. Okay, so the frequency is how fast this cosine is oscillating, the sinusoid is oscillating. Okay, so if I have a larger value of omega, that means a small change in t is going to produce a large change in this argument. Okay, so larger omega going to make this cosine oscillate more quickly. That's what frequency tells us. It tells us how fast something is oscillating per time. Okay, and what's this last one here? That is the phase. And that just provides an offset for the sinusoid. So if I don't have a phase, if I plug in t equals 0 at time 0, I'm going to get cosine of 0, which is 1 times a. So I'm going to always start at the peak of the cosine, but with that phase, it allows me to shift it. So if I wanted to draw a picture of this really quick, it looks something like this, right? Where these values here are plus and minus a, that's the amplitude. The phase is sort of controlling like how much this cosine is shifted by from the peak, which is where it would be if there was 0 phase. If there was 0 phase, my vertical axis would go straight through that peak, but there could be some non-zero phase. So I'll just sort of generally label that like that. And the frequency is sort of having to do with how fast this thing is oscillating. Okay, so you can see like one period, we're going to talk about period later in the class in more depth, but how far does it take for the cosine to go from peak to peak? If I had a higher omega, it would be oscillating more quickly, so that that distance would shrink, okay, versus a smaller omega, it would be oscillating more slowly and that distance would grow. Okay, so we're going to talk about this more later in the class. I'll erase it for now. I'm sure it's review for most of you, but that's what we're talking about here, amplitude, frequency, and phase. And that goes into our RLC circuit, and we get out something. We don't know what. We don't know what. So we're going to get out something. One more note I want to make is that omega in this class is in radians per second. Okay, it's angular frequency. And you should compare that to hertz, which is also a common measure of frequency. And this is cycles per second. Okay, so if you think about it, like if I'm kind of going around and around in a circle, if I go around in one cycle, how many radians have I gone through? I've gone through 2 pi radians, right? There's 2 pi radians in a circle. Okay, so every one cycle gives me 2 pi radians. And so we can see that radians per second, the unit of omega, we're going to mostly be dealing with omega in this class, is just 2 pi times the hertz cycles per second. Okay, so there are some points where we might want to convert between them for different applications. So always good to know what we're talking about. Okay, so that's the general setup. And for an RLC circuit in sinusoidal steady state, when our input is a sinusoid, okay, we know kind of all of the signals involved anywhere in a circuit are also going to be sinusoids. In particular, our output is also going to be a sinusoid with the same frequency. Okay, so what could we do? Well, we could just analyze things as it is, just put the sinusoid into the circuit and do all the computation, all the math, all the analysis, and get our output, which is going to be some sort of sinusoid with this frequency omega. But some people came along and said, wait a second, if I know that all of my sinusoids in the circuit have that frequency omega, let me try and save myself some time writing down omega t everywhere and kind of get rid of that. I'll keep it in the back of my head that everything in this circuit has frequency omega, but I won't keep writing it everywhere. All I'm really concerned about is the amplitude and the phase. And that is where phasors come in. That's exactly what phasors do for us. So let me just explain what they are. So if I have some signal f of t, and it's going to be my general, whoa, I don't know why that keeps happening. And it's going to be my general sinusoid here. Okay. Well, I want a way mathematically to make sure I really precisely understand what I mean by just taking the amplitude and the phase. And so what we do is we write this as the real part of what? Well, we can use Euler's formula, right? Cosine is the real part of Euler's formula. Remember, e to the j x is cosine of x plus j sine of x. So the real part of this is the cosine of x part, and that's exactly what I have here. X here is omega t plus phi or phi. Okay, I'll probably use both. I'm not sure which one's right. But a times cosine of omega t plus phi. Okay, if omega t plus phi is my x, I can write this as the real part of a e to the j omega t plus phi. Right, just use Euler's formula, expand this like that, take the real part, and there you go. You have exactly the cosine that we started with. Oh, and by the way, I should say that a here, we're going to be a real number. The amplitude of this sinusoid is going to be real. Okay, so we used Euler's to get that. And with this expression written down now, we can define what the phasor is. So the phasor of f of t is going to be just the amplitude. I'm going to get rid of this e to the j omega t. And I'm going to keep the e to the j times phi. Okay, so it's going to be a e to the j phi. Okay, so that's the phasor. We've kept the amplitude and the phase, and we've written it in this form. And you know, I'm sure you're familiar with complex numbers, and there's also a video about this, so you should definitely watch if you want to review. But this is just a complex number. That's all a phasor is. It is simply a complex number, nothing more, nothing less. It is a complex number that, with all of our understanding of what we want it to do for us when we're analyzing circuits, you know, we understand that this complex number is representing the signal, but it's simply a complex number. That's all. Okay, it does not change with time. There's no t here at all. It is just a complex number encoding those two pieces of information we want, the amplitude and the phase. Okay, and so just some notation real quick. We're going to write this relationship as f of t. It's going to be a cosine omega t plus phi. And we're going to use this double arrow to say what its phasor is, a e to the j phi. And typically I'm going to use capital letters to denote phasors. Okay, so if I have a signal f of t, I'll usually denote its phasor as capital F. If I had, x of t, I'd use capital X and so on. Okay, so now let me just write down what I said in words, that phasors, what do they really do for us? They hide the term e to the j omega t, right? All we did was hide this term because we know it's going to be in every single signal in our circuit. We know all of our signals can be written as cosine of omega t because we're in sinusoidal steady state. So why should we keep writing that? All we really care about is the amplitude and phase. So phasors hide that term that we already know is in everything. Okay, they hide that term in that expression because, I'll just write it down, that term appears in every signal. Whoa. In an RLC circuit with single frequency input. That looks something like this. Okay, so as long as you put in a sinusoid with just one frequency omega in the input, then we know every signal is going to have this term, at least if I express it like this as the real part or something. Okay, so why keep writing that? That's the whole point of phasors. It's just a bookkeeping method to make our job a little easier writing wise. Actually, believe it or not, when I learned this in school a while ago, I don't even think we used phasors. I think we analyzed a lot of the time just using these cosines. And yeah, we had to write a little more, but in some ways it was, kind of more clear exactly what was happening. Using phasors, you always have to keep in the back of your head, I'm just, using this kind of notational bookkeeping method to not have to write everything. You have to always remember, we actually have some sinusoidal inputs going through our circuit. We just only care about the amplitude and the phase. Okay, and also just make another note here. We can convert between the time domain, and by that I just mean functions of time like f of t, the time domain and the so-called phasor domain. I just mean the phasors of all those signals, as long as we know the input frequency, omega, right? Because if I just gave you this phasor, you wouldn't know what the frequency is. You wouldn't know what omega is. Okay, so you have to keep in the back of your head what the omega was, what the input frequency was for the time function you put into your circuit whenever you're using phasors that you can always convert back in the end. Okay, so let me just now review the kind of steps we use to analyze inputs and circuits in sinusoidal steady state, and then we'll do an example. Okay, so right now I'm going to talk about the method to find the input output relationship of an RLC circuit in sinusoidal steady state. Okay, so like I said, we're going to have our box here and we're going to take this to be an RLC circuit. Okay, and then we need to have some input. So I'll just hook this input up as a voltage source somewhere in the circuit. I'll just kind of abstract it as, this drawing, it goes into some circuit. And I'm going to call that V sub I of t, the input voltage source in this case. And we're going to have an output here. We're going to probe the circuit somewhere and have our output voltage function of time v sub o. Okay, and there's going to be no other sources in the circuit. And by the way, don't be afraid if you're kind of rusty on circuits. They're not my strong suit either, and they're not going to appear a ton in the class. In this class, they're mostly used as a gateway to kind of get us used to some ideas that we're going to then talk about in a much more general setting than just circuits very soon in the class. Okay, so circuits are going to mostly be at the start of the quarter, and then we're going to make things a little more general. But okay, so we have a circuit for now. And how can we try and find the input-output relationship? Well, we can follow a few steps, actually. Breaks up nicely into steps. So step one is we're going to phasorize, as I like to say, the input. Okay, so we're going to take our input, convert it to the phasor domain, find its phasor. Step two, we're going to phasorize the circuit. And what does that mean? i.e., that is, we're going to change all of the R's, L's, and C's to their impedances. Okay, so resistors, what's the impedance of a resistor? Well, it's just the resistance. What's the impedance of an inductor with inductance L? It's just J omega L. And what's the impedance of a capacitor, a capacitance C? It's 1 over J omega C. Okay, so we're going to take our circuit and change all of these circuit components. We know it's an RLC circuit, so this is all we have. We're going to change them all to their impedances. And then once we do that, we can move on to step 3, which is to solve the circuit of impedances now, as if it were a resistor network. All right, I'm sure you've all seen this before. Once we have it in terms of all the impedances, we can combine the impedances as if they were resistors in series and parallel, whatever we have. And then finally, our step 4 is once we do that, we can then find the output in terms of the input, and then we can unphasorize or convert back the output. Okay, so that's the general setup for how to solve this type of question. So now let's do an example, which I'm sure will look familiar. Okay, we're going to follow these steps, do this example. So we want to find the output voltage if the input voltage is 4 cosine of 2t minus pi over 4. And I'm going to draw the circuit in a second. There's going to be a resistor. I'm going to have that be 4 ohms. There's going to be a capacitor. I'm going to have that be 1/8 of a farad. And what does the circuit look like? Well, we're going to have our input voltage. We're going to have a resistor. We're going to have a capacitor. And we're going to have our output voltage over here. Okay. So let's do it. So what do we want to do? Well, we want to take our input and phasorize it. We want to take the circuit, phasorize it, solve everything, and then unphasorize whatever we get. Okay, so let's phasorize the circuit because I just wrote it. We have it here. Let's just do that. We know we have to. Okay, so when we phasorize it, I'm going to have my voltage source here, but I'm just going to write the phasor, and that's supposed to be a capital V. Okay, the phasor for V sub I, capital V sub I. Then I'm going to have a resistor here. We know the impedance of a resistor is just R. I'm going to have a capacitor here. That impedance is 1 over J omega C. And then our output is just going to be the phasor V sub I. Okay. All right. So now how do we find the output phasor in terms of the input phasor? Well, I think it should be pretty clear. We're going to use a voltage divider. And I'm going to keep the circuit solving techniques pretty simple in this class. I think I'm probably mainly going to use voltage divider, maybe current divider somewhere, but it's going to be nothing complicated. I think the circuit solving, you should have no trouble with. That's not the point of this class. We're going to try and make that easy. It's going to be the ideas and the understanding that's new in ECE 45 that I really want you guys to know. So the circuit solving, I'm going to try and make really, really easy in all of the quiz questions and just everything in general. Because that's not the point. You already did that in 35. Now we gotta talk about new stuff. Anyway, so we have a voltage divider. So we know our output voltage phasor is going to be our input voltage phasor times what we get with the voltage divider. And what do we get? Well, we're going to have this impedance divided by the sum of the two impedances. So 1 over j omega c divided by r plus 1 over j omega c. Okay, I don't like having the 1 over j omega c, so I'm going to multiply top and bottom by j omega c. So I get the input phasor times 1 over 1 from that guy plus j omega rc. Okay, so that's what we get so far. So now I need to find what this input phasor is. Okay, so what's the input phasor? Well, first of all, I always like to take note of what frequency I'm working with. Frequency omega is 2 here. Okay, I like to always write that down just so I don't forget. And I remember that through this whole process, we're kind of keeping this omega in the back of our head. We're going to work with phasors, so we just work with the amplitude and phase of our sinusoids. We always got to remember that this omega equals 2 in this case is kind of there for all of the phasors we're working with. Okay, so what would be our input phasor? Well, you can see the amplitude is 4. You can see the phase is negative pi over 4, so we get 4 times e to the negative j pi over 4. And now what do I get for this expression here? Well, I'm going to have 1 over 1 plus j. Okay, and now what's omega? Well, it's 2. You can see where the omega even shows up in this expression. So you really have to, realize that we're dealing with omega equals 2 here. Times the resistance, which was 4, times the capacitance, which was an 1/8. Okay, so I get 4 e to the negative j pi over 4, 1 over 1 plus, that's 8 over 8, so just 1 plus j. And now we want to get this in terms of a phasor, okay, so some complex number in polar form, so that we can convert back, right, so that we can unphasorize. So how do we do that? Well, this is already a number in polar form. That's nice. We got to change this guy. Okay, so we see a 1 plus j, so we got to convert that to polar form. It's in rectangular form right now. So I can draw a complex plane real quick. And I have this point right here, 1 plus j. So I want it in polar form, so I need the magnitude and the phase. Okay, what's the magnitude? Well, you can see this is just a 45, 45, 90 triangle, right? Both side lengths are 1, so this magnitude of that complex number 1 plus j has to be root 2. And you could also get it as just square root of imaginary part squared plus real part squared, so square root of 1 squared plus 1 squared, square root of 2. And what's the angle? Well, you can see, just kind of geometrically, visually, that should be 45 degrees or pi over 4 radians. Okay, but of course you could also use inverse tangent. But I find it a lot easier actually. And again, I'm going to, probably for the most part, have pretty simple complex numbers here. Like the angles are probably going to be pi over 4, pi over 2, pi over 3, pi over 6, like classic right triangles. So you can kind of easily convert between rectangular and polar form most of the time. Okay, because again, that is part of the class, but we have a lot of more important ideas to talk about. So I want to try and make that sort of as simple as possible. Okay, so now we have two complex numbers. We got to divide them, but that's really easy to do in polar form, right? Because I just take 4 divided by root 2. Well, 4 is just root 2 to the 4th power. So 4 divided by root 2 is root 2 to the 3rd power, which is 2 root 2. And then I have e to the negative j pi over 4 divided by e to the j pi over 4. When you divide by a e to the j times some angle, you just subtract that angle from the thing you have on the top. You could also think of it as it's this times e to the negative j pi over 4 if I bring it to the numerator, whatever you like. But in any case, we get e to the negative j pi over 2. Oops, pi over 2. Okay, and there's our output phasor. That's great. So we can convert back now. That means our output time signal, we're going to unphasorize. Well, here is my amplitude, 2 root 2. Then I have cosine of what? Omega t, but remember omega is 2. So I have 2t. And then minus pi over 2, that is my phase. This is a perfectly fine answer, but think about it. If I have cosine, okay, and I shift it to the right by pi over 2, then it looks like this. It's just sine, right? Cosine of 2t minus pi over 2 is just a cosine shifted to the right by pi over 2, and that gives you a sine. Right, if I start with cosine and I shift it to the right by pi over 2, it just becomes a sine. Okay, so this is actually just 2 root 2 sine of 2t. Okay, so there you go. So that's it. So we were given an input in time. We were given a circuit with these two components. Okay, and we phasorized everything, solved it, got our output phasor, and then converted back to the time domain to get our output in time. All right, so hopefully that was a good review. And in the next video, we're going to start talking about frequency response of RLC circuits.